Deep neural networks. In this unit, we will explore the fascinating world of deep learning and neural networks. We will cover various topics including the introduction to neural networks, training neural networks, activation functions, loss functions, hyperparameters, and more. Each topic will provide a comprehensive understanding of deep neural networks. The perceptron is a fundamental building block of neural networks. It is an algorithm used for supervised learning of binary classifiers and forms the basis for more complex neural networks. Single-layer perceptrons are the simplest form of neural networks, capable of learning only linearly separable patterns. They are useful for basic classification tasks. Multi-layer perceptrons, on the other hand, can learn more complex patterns by using multiple layers of neurons. This allows them to solve more intricate problems. The perceptron function maps input values to output values using a learned weight coefficient. Activation functions play a crucial role in determining the output of the perceptron. Perceptrons are powerful tools for solving complex problems, but they also have limitations such as time-consuming computations and difficulty in handling non-linear data. Now, let's delve into multi-layer feed-forward networks, which are more advanced than single-layer networks and can handle more complex tasks. Single-layer networks are simple and limited, while multi-layer networks can extract higher-order statistics and solve more complex problems by using multiple hidden layers. Multi-layer perceptrons are used in various applications such as medical field, speech recognition, and data processing. They are essential for solving problems that require supervised learning. Training neural networks involves backpropagation and forward propagation. These processes are crucial for adjusting the weights and biases to minimize errors. Forward propagation is the process of moving inputs through the network to generate an output. It involves calculating the weighted sum of inputs and applying activation functions. Let's look at an example of forward propagation. We calculate the weighted sum of inputs and apply the activation function to generate the output. To improve the performance of our neural network, we use backward propagation to adjust the weights and biases based on the error calculated during forward propagation. Backward propagation involves calculating the partial derivatives of the error with respect to the weights and biases. This helps in minimizing the total cost and improving the network's performance. In this example, we calculate the partial derivatives for the second training example and update the weights and biases accordingly to minimize the error. During each epoch, the forward and backward passes are repeated to adjust the weights and biases continuously, improving the network's accuracy over time. Activation functions are crucial for determining the output of neural networks. They introduce non-linearity, allowing the network to learn complex patterns. Activation functions decide whether a neuron should be activated or not. They transform the weighted input into an output signal, enabling the network to learn and make decisions. Without activation functions, neural networks would only perform linear transformations, making it impossible to learn complex tasks. They are essential for adding non-linearity to the network. Let's explore the three types of neural network activation functions: binary step, linear, and non-linear activation functions. Each plays a crucial role in determining the output of a neural network. The sigmoid function is a popular activation function that outputs values between 0 and 1, forming an S-shaped curve. However, it has limitations, such as vanishing gradients, which can make training deep networks difficult. The tanh function is similar to the sigmoid function but outputs values between 1 and 1, providing a stronger gradient for learning. It helps in centering the data but still suffers from vanishing gradients. The softmax function is used for multi-class classification problems. It converts logits into probabilities, ensuring that the sum of the probabilities is equal to 1, making it ideal for output layers and classification tasks. Imagine we have 5 output values. The softmax function will convert these values into probabilities that sum up to 1, helping us determine the most likely class for a given input. ReLU is a widely used activation function that outputs the input directly if it is positive, otherwise, it outputs 0. It helps mitigate the vanishing gradient problem but can suffer from the dying ReLU problem. ReLU accelerates convergence and is computationally efficient, but it can lead to dead neurons where some neurons never activate. This is known as the dying ReLU problem. Leaky ReLU addresses the dying ReLU problem by allowing a small, non-zero gradient when the input is negative, thus enabling backpropagation even for negative inputs. Parametric ReLU is a variant of leaky ReLU that introduces a parameter to control the slope of the negative part of the function, allowing the model to learn the most appropriate value during training. In summary, activation functions like sigmoid, tanh, ReLU, and softmax each have their unique advantages and limitations. Choosing the right activation function depends on the specific requirements of your neural network model. Here are some commonly used activation functions, including step, signum, linear, ReLU, sigmoid, and tanh, each with its own range and properties. Choosing the right activation function depends on the type of neural network and the specific task. For example, ReLU is often used in hidden layers, while softmax is used for classification tasks. Now, let's dive into loss functions, which are crucial for measuring the difference between the predicted output and the actual output of a model. Loss functions help evaluate how well your algorithm models the data. They can be categorized into classification and regression losses, each serving a different purpose in model training. Let's focus on loss functions for regression problems, which measure the difference between predicted and actual values. There are several types of regression losses, including mean absolute error, mean squared error, root mean squared error, and mean bias error. Each has its own advantages and use cases. Mean absolute error is a simple and computationally inexpensive loss function that measures the average magnitude of errors in a set of predictions without considering their direction. MAPE calculates error in terms of percentage, making it independent of the scale of the variables. However, it can be problematic when the actual values are 0 or close to 0. Mean squared error penalizes larger errors more than smaller ones, making it useful for models that need to minimize large deviations. However, it is sensitive to outliers. L1 loss is more robust to outliers but has discontinuous derivatives, making it less efficient for optimization. L2 loss, while sensitive to outliers, provides a more stable solution with continuous derivatives. RMSE, or root mean square error, is a linear scoring method that gives more weight to larger errors compared to MAE. It is less extreme for larger values but is sensitive to outliers. When moving to the left of a maximum, the gradient changes from positive to negative and vice versa for a minimum. At the point of maximum or minimum, the gradient is 0. Huber loss is a combination of MSE and MAE, providing a balance between the two. It is quadratic when the error is small and linear when the error is large, making it robust to outliers. Huber loss is preferred for training neural nets due to its robustness to outliers and smoother gradient near the minima. It combines the benefits of both MSE and MAE. Log-Cosh loss is the logarithm of the hyperbolic cosine of the prediction error. It is smoother than MAE and approximates MSE for small values, making it a balanced choice for regression problems. Quantile loss helps in predicting quantiles by minimizing the quantile regression loss function. It is useful for understanding the distribution of predictions. This plot shows a comparison of different loss functions, including MSE, MAE, Huber, Log-Cosh, and quantile, highlighting their behavior with predicted values. Loss functions can be categorized into those used for classification and those used for reconstruction, each serving different purposes in machine learning models. Logarithmic loss, or binary cross-entropy, measures the accuracy of a classification model by comparing predicted probabilities to actual class labels. It is crucial for binary classification problems. The red line represents class 1, where higher predicted probabilities lead to lower loss. The black line represents class 0, showing the inverse relationship between predicted probability and loss. Hinge loss is used in support vector machines to create a decision boundary with a margin. It penalizes misclassified points based on their distance from the margin. Hinge loss can be explained by the distance of points from the decision boundary. Correct predictions have 0 loss, while incorrect ones are penalized based on their margin distance. Focal loss addresses class imbalance by focusing on hard-to-classify examples. It adjusts the loss contribution based on the confidence of predictions, improving model performance on imbalanced datasets. Focal loss is defined with parameters alpha and gamma, which control the focus on hard examples. It combines cross-entropy loss with a modulating factor to downweight easy examples. Focal loss helps in handling class imbalance by emphasizing hard examples during training. It is particularly useful in object detection and other tasks with skewed class distributions. KL divergence measures the difference between two probability distributions. It is used to compare the predicted distribution with the actual distribution, though it is not symmetric. Exponential loss, used in AdaBoost, focuses on misclassified points by increasing their weight. 0-1 loss is the simplest, counting only the number of mispredictions. Hyperparameters are crucial for controlling the learning process of algorithms. They include learning rate, regularization, momentum, and sparsity, each affecting model performance differently. Key hyperparameters include learning rate, batch size, momentum, and weight decay. Adjusting these can significantly impact the training and performance of machine learning models. Hyperparameters influence the model's ability to learn and generalize. Proper tuning is essential for achieving optimal performance, as they affect the training dynamics and final model accuracy. A neural network learns or approaches a function to best map inputs to outputs from examples in the training dataset. The learning rate hyperparameter controls the rate or speed at which the weights of the model are updated during training. Given a perfectly configured learning rate, the model will learn to best estimate the function given the number of layers and the number of units in each layer. Usually, a large learning rate leads the model to learn faster, at the cost of arriving at a suboptimal final set of weights. A smaller learning rate may allow the model to learn more optimal or even globally optimal set of weights but may take significantly longer to achieve. Since gradient descent can only find local minimums, a lower learning rate may result in bad performance. To do so, it is better to start with the random value of the hyperparameter and increase model training time, but there is a sweet spot at which the gradient descent can manage the training time. There are lots of optimizers for the same task, but the optimizer is perfect. It depends on some factors like size of training data, and optimizer gradient descent will be slow whenever the gradient is small, then it is better to go with a higher learning rate. Momentum in neural networks is a variant of the stochastic gradient descent. It replaces the gradient with a momentum, which is an aggregate of gradients. The momentum factor is a coefficient that is applied to an extra term in the weights update. Besides other, momentum helps to speed up learning and to help the training to be faster than SGD. Local minima can be avoided as we reach global minima due to the momentum involved. Regularization, in the context of neural networks, is a process of preventing a learning model from getting overfitted over training data. It involves a mechanism to reduce generalization error but not the training error. The regularization method optimizes the fitting ability of a learning model to predict correct output for previously not seen data. L1 regularization is the process of preventing a learning model from getting overfitted over data. In L1 regularization, a penalty is added to the loss function to prevent the learning model from getting overfitted, which is the sum of the absolute value of weights. Ordinary least square or OLS is better than L1 regularization in identifying more significant features that can have a heavy influence on the output. L1 regularization is robust in dealing with outliers. It creates sparsity in the solution. Similar to L1 regularization, L2 regularization introduces a new cost function by adding a penalty term to a loss function called an L2 weight penalty. The larger the value of this coefficient, the higher is the penalty for complex features of a learning model. Dropout is a method in which nodes in a layer are randomly selected and dropped to make the learning model more generalized so that it won't be overfitted. Sparsity in this context refers to the fact that some parameters have an optimal value of 0. The sparsity of L1 regularization is a qualitatively different behavior than arises with L2 regularization. The sparsity feature used in L1 regularization has been used extensively as a feature selection mechanism in machine learning. Gradient descent adjusts parameters to minimize particular functions to local minima. In linear regression, it finds weight and biases, and deep learning algorithm uses the method. The algorithm objective is to identify model parameters like weight and bias that reduce the cost function to a minimum. In machine learning, a gradient is a derivative of a function that changes if you change the input variable. Knowing the slope of a function in mathematical terms, we measure how much the output of a function changes when you change the input variable a little bit. There are different types of gradient descent like batch gradient descent, mini-batch gradient descent, and stochastic gradient descent. In this process, we use the whole dataset in each iteration. If you have only 100 data points, it will be okay. But if you have 10,000 or 100,000 data points, then you need to run a 1000 iteration for convergence. Computation will be really fast and easy. To solve that problem, instead of using all 100,000 data points, a random data point can be chosen for each iteration. Computation will be really fast. This is called stochastic gradient descent. Components of gradient descent include learning rate, activation function, and random initialized weights. The steps involve initializing weights, picking a suitable learning rate, calculating the output, choosing an activation function, and updating the weights using gradient descent. Local minima and maxima are points on a graph where the function reaches a minimum or maximum value, respectively. On a graph, many local maximum-minimum values may be possible, but there will be only one global maximum-minimum value. Global minima and maxima are the absolute minimum and maximum values of a function on the graph. The global minimum value is the lowest point on the graph, while the global maximum value is the highest point. Imagine you are a skier on a mountain. You want to find the lowest point around you, i.e., finding the place with minimal altitude. Mathematically, the slope is the derivative. Positive derivative means go to the left, and negative derivative means go to the right. Deep feed-forward networks, also called feed-forward neural networks or multilayer perceptrons, are the quintessential deep learning models. These models are called feed-forward because information flows through the function being evaluated from x, through the intermediate computations used to define f, and finally to the output y. Deep feed-forward networks are extensions of simpler models that can solve more complex tasks. They are composed of multiple layers, each transforming the input data into a more abstract representation. The final layer provides the output, which is compared to the target during training to adjust the weights. Training a deep feed-forward network involves using a loss function to measure the error between the predicted output and the actual target. The network adjusts its weights to minimize this error, using techniques like backpropagation and gradient descent. Solving the XOR problem by learning a representation. The linear model cannot solve this problem. The neural network can transform the space represented by the features extracted by a neural network. In other words, the nonlinear features have mapped both x1 and x2 to a single point in feature space. The backpropagation algorithm is used to train neural networks by adjusting the weights to minimize the error. It involves calculating the gradient of the loss function with respect to each weight and updating the weights in the opposite direction of the gradient. The error backpropagation learning algorithm is a crucial method for optimizing neural networks by computing the gradient of the loss function. It adjusts the weights to minimize errors and improve accuracy. Backpropagation is essential for deep neural networks, allowing them to learn and adjust weights to minimize errors. It involves calculating the output for each neuron and adjusting weights to decrease the error. Vanishing and exploding gradient descent are critical issues in training deep neural networks, affecting the learning process and model performance. Vanishing gradients occur when gradients become very small, making it difficult for the network to learn. This often happens with activation functions like the sigmoid function, which compresses input into a smaller output range. Exploding gradients happen when gradients grow too large, causing unstable learning. Proper weight initialization and normalization techniques can help mitigate these issues. Sentiment analysis involves determining the sentiment behind text data, such as reviews or social media posts, and categorizing it as positive, negative, or neutral. Sentiment analysis works by linking text to a database, processing it through natural language processing techniques, and using machine learning algorithms to classify the sentiment. Sentiment analysis software uses advanced techniques to analyze text conversations, providing insights into emotions and opinions. Top software includes Google Cloud Natural Language API, Lexalytics, and IBM Watson. Thank you for your attention.